Good afternoon, everyone. Our sincere thanks to Indian Nuclear Society to give this platform to speak on the safety research regulatory decision making for the reactors. I have chosen for water reactors since our reactor design and development group primarily worked on the light water reactors or the heavy water reactors. So I will be speaking on the current status and way forward. Start with the basic definition of the research, which is the purpose of generating new knowledge through the process of discovery. And scientific research involves diligent inquiry and systematic observations of the phenomena. Most scientific research needs experimentations, which often testing the effect of changing conditions of the results. And we see that there are two categories of the research. One is the basic research, and another is the applied research. The objective of this basic research is to gain more comprehensive knowledge or understanding of the subject under the study without specific applications in mind. For example, the study of spray. So spray, the basic researchers, they do the study on the spray with a varied kind of spray droplet size, interaction, etc. But whenever it comes to an applied research, it is very much industry oriented. Like the spray in the car wash or the spray in the nuclear containment, that would be entirely different. The characteristics would be entirely different. So with respect to the industry pursuit, the research gets oriented. Now, with respect to our nuclear domain, the safety research that is being carried out between these three agencies. One is the utilities, second is the regulator, and third is the research institutes. So if you see, the primary objective of the utilities is to carry out research to meet the design requirement as per the regulatory guidelines. Whereas the regulators, they try to carry out the research to meet set or review the design acceptance criteria that are coming over the edges, or some new criteria they need to set up so that the utility can meet those criteria. Now the research institutes, they work as a feedback either from the utility or from the regulator. Sometimes the utility, they require some particular research to be carried out in the research institutes, or the regulator wants some research to be carried out at research institutes. So the research institutes carry out, first is the basic research, then the applied research to support utility, either utility or regulator or both. And third is the capacity, that is knowledge and technology building for future demands. Since the kind of research demands keep coming, so they need to also cope up with the future needs. Particularly to focus over here, why regulatory research is required for. The research aims to close the identified gap areas in different fields in nuclear safety for a fresh design and aging plants. The research aims to reduce the order of uncertainty in the selected safety and acceptance criteria. The research aims to quantify the acceptance criteria rather than keep the criteria subjective. Many places you will find the criteria are given subjective, but obviously a dispute comes whenever the criteria is put as a subjective matter. Then the research intends to evolve new acceptance criteria with respect to the ever-evolving technology, environment, and different situation needs. So as we know that environment and situations are changing over the time, so there's always a need to update the new acceptance criteria. Now, I will show you some glimpses of safety research in regulatory decision making. Basically, if you see the the support that is given to the designers as well as the regulator over decades by Reactor Design Development Group is enormous. So with that respect, I will just touch upon of the few activities that helped the designers as well as the regulator for decision making. See, this is with respect to the criticality safety, the shut-off rod testing facilities. So the shut-off rod testing facility, two examples are given over here. One is the prototype drive mechanisms for our Dhruva reactor, APSARA reactor. Another is with the 500 megawatt PHWRs. So these testings are, as you know, the reliability of these systems are at most required, and to meet a certain reliability numbers or this certain reliability targets, all the design and experimentation are to be conducted in a repetitive manner. So this is achieved at our Bhabha Atomic Research Center. Coming to another critical safety exercise, this is a test facility for moderator flow and liquid poison distribution. As you know that for PHWR as well as AHWR, the secondary shutdown system is the injections of poison into the moderator. So these test facilities were evolved, and see, at the time of the licensing of these reactors, so the demonstration of such activity needs to be performed. So these facilities need to be preserved till the regulators get the satisfactory response. Coming to this, this is very off-late activity. This is the assessment of effectiveness of spray cooling on decay heat removal from coolant channel under postulated LOCA with unavailability ECCS. This is fairly applicable for the old reactors, where the spray cooling under such postulations, as we know, the moderator gets dumped, and the spray cooling is the media which is supposed to remove the heat from the channels. So you can see this is especially, this is a spray nozzles that is currently present in RAPs and MAPs. These are the central locations of the calandria, which sprays from the top, and it is having basically 13 nozzles. And this is a hub in which the 13 nozzles are being placed. And this is the spray nozzles which are kept near the end of the calandria, so to cool the roll joints. So under circumstances like postulated LOCA with loss of ECCS conditions, how the channels are going to get cooled, that is one regulatory issue was there. So that was addressed through the experiments, and the experiments, if you see, the channels, which is a heated channel of simulating the PHWR channel, that is pressure tube, calandria tube, etc. So this is when it is subjected to some power. You can see the temperatures, they are stable. Stable means whatever is the injected power and whatever is the spray flow rate. So the spray flow rate is able to take out the heat. So that shows the stabilization in the temperature. Similarly, when the power is jacked up, you can see the stabilization of temperature. Again, when the power is jacked up, so this is around 3% of the decay power. So again, the temperature is stabilized. So this shows that at different decay power levels, with this spray, it is able to take out the decay power. So this confirms that the channel is coolable under the postulated accident conditions. Now this is with respect to the structural safety. So as we know that a large number of cycles of large magnitudes are expected during the severe earthquake events. So the structural safety program was floated in somewhere around in 1980s in our reactor design and development group. And you can see a very large setup that this experiment was conducted at ACRC, ACRC. So this is a cyclic fracture test, and the rules are developed. Basically, today the ASME rule is based on the strength, and it is not based on this the very frequent cycles of high magnitudes which are supposed to come during the earthquake. So rules developed for improved integrity and safety assurance under the severe earthquake event. Coming to the next one, this is the integrity under extreme cyclic loading earthquake. So the rules are developed for improved assessment of ratcheting and fatigue. You can see that through wall puncture has happened and then water is getting sprayed off. So this is also a situation where the rules need to be developed for an improved assessment. Coming to another aspect is that seismic safety. The soil amplification studies, basically with the soil liquefations. So this study is being attempted. So you can see the shake tables setup of soil laminar shear blocks. And here you can see the amplification factor versus height of soil column. At different columns, the acceleration is being measured. So this is the height of the column, and this is the amplification factor. So it is concluded from this test that the soil column frequency was nearer to 7 Hz. Basically, this kind of information is required to generate the shear modulus and shear strain profiles or the relations. This particular slide shows the development of high temperature clad bus correlation. So our PID colleagues, they developed this burst correlation with Indian PHWR clad tubes. So far, whatever is given in the SGD6 guide, that follows this Erbacher relation. So you can see with the Indian clad tubes, the correlations for burst correlations at different alpha plus beta and beta regimes, they are widely varying. So this brings, kind of establishing our own correlation. So far we are depending due to the lack of information generated at our end, that we were working always with the PWR clad tubes informations. Now with the PHWR clad tubes, as the fabrication route differs, so the grain orientations as well as the creep of these clad tubes are widely found to be different than the PWR clad tubes. This is a particular experimentation that was done on the PHWR channel integrity under LOCA with unavailability of ECCS. So far we were banking on the Canadian experimentation and Canadian inference that coolant channel survives under such postulated conditions, that LOCA with unavailability of ECCS and moderator is able to take out the heat. So we performed the experimentation for a full length coolant channel with the pressure tube, calandria tube, and with the internal weights that is equivalent to all 10 fuel bundle weights, so that the stiffness is well maintained, the stiffness is well simulated, and you can see with the contact that, and along with the garter springs, so with the contact gets established at several locations, and then there is once the PT contracts the CT, the temperature starts dropping in, and finally the temperatures all get cooled down with the moderator as a heat sink. And this is done at the 3% decay power level, which is expected of the time the LOCA without unavailability of ECCS is situation arise. And this is another experiment. The same tube is now filled with 20 bar pressures, and the sagging at 3% decay power level is simulated. So you can see this large scale experimentation with a full length channel of 5.6 meter. We could able to establish the moderator which acts as an effective heat sinks, and it is also experimentation done to get the creep correlations, which shows that our pressure tubes start sagging much earlier, that is around 650 degrees centigrade for especially the sagging part, that it starts sagging at 650 degrees centigrade against the Canadian tubes, which starts sagging at 850 degrees centigrade. So we will get a very early contact, and the heat removal from the steam voided channel becomes very effective. Another gray area was there, that is when the subsequent to this channel sagging, that when there's a channel sag or channel balloon, the pressure tube contacts the calandria tube, and what would be the order of contact conductance. So the contact conductance was evaluated with a very precise experimentation, and you can see the pressure tube and calandria tube samples generated by our NFC colleagues. And this is the contact conductance that was established. You can see that the experimentation done with these pressures, that is contact pressures, from 0.6 megapascals to around 6 megapascal. The variation is that this is responsible when the calandria, when the pressure tube is sagging, and this is for the ballooning. When you have the ballooning at high pressures, the contact pressures becomes very high. So this study is able to generate a correlations with respect to the temperature and the contact pressure, as well as the material hardness. This is another gray area which was prevailing for a long time, that PHWR channel disassembly, when we are going to the deck B situations where moderator is getting boil off, and that this is an unmitigated situations of severe accident in PHWR scenario. So when the channels are getting exposed, so there's a concept of channel disassembly. Channel gets disassembled with after a certain temperature and the strain rates which comes due to the sagging. So this is a 3-layer pressure tube, I should not say pressure tube, it is pressure tube and calandria tube, that is 1:3 scale. Again, thanks to NFC colleagues who could able to make pressure tube and calandria tube of 1:3 scale. That means diameter and the thickness are reduced by 1:3. Otherwise, the stiffness of the systems cannot be maintained. So the experimentation was done, and it was found that you can see the temperature history as well as the deflection of the top row of channels. So a disassembly criteria was evolved, that it was observed when pressure tube temperature attaining 1,000 degrees centigrade with sufficient steam oxidation, the channel disassembles, and one disassembled piece is around 4 to 6 bundles length. So that gives a very sufficient idea that how the channel disassembly takes place. Subsequent to this disassemble, there's a question that how much hydrogen generation to be considered. See, this is very important from the hydrogen generation source term point of view, so that your recombiners are numbered and organized accordingly. So if you consider that the pieces of channels which comes down and it is in the horizontal position, there's a very least chance that steam will get ingressed and the internals of the channels will get oxidized. So the experimentation was done. This is the channel simulator with all zircaloy material along with all spacers, so that the exact resistance of the flow path of the steam could be able to simulate it, and the hydrogen generation with the radial power variations of the fuel pins. Now you can see it is concluded that if you keep the channel in the horizontal position and the tilt positions, if you have the tilt positions, then there is a larger steam flow, but of course, it is expected that hydrogen generation will be high, but nevertheless, the cooling is also there. So it is found that no significant rise in oxidation beyond 20-degree inclination. So this is also very important observations. How so quickly? How much? Oh, time flied up. That's very. I will try to manage it. So the containment safety is a hydrogen studies. So recently this particular study has been done. That is the erosions of the hydrogen layer. See, today we know that the regulatory limitations is 10% volume by volume. So if you have the hydrogen along with the injections of the air, so after some time the hydrogen concentration comes down to quite low, that is lower than the deflagration limit. Now with the capacity building at our center, we are having a series of design and analysis softwares which are evolving over the decades and which are still evolving. Reason is that due to the arrival of the new technology and the capacity of the high-end computing machines. And this is one of the latest generation accident analysis integrated code, which starts from the reactors, starting from the reactor accident initiation up to the dose, public dose calculations, up to 7 days, 1 year, 3 year, 4 year, whatever is your wish. This is also the capacity of our reactor design development group, which is supporting over the years and decades. So I will just rush through the capabilities of our, rather the strength that has come over the years. This is also very interesting now, the human reliability analysis studies, which is using the machine learning approach. So the human error probability is being estimated with the virtual environment. You can see the virtual environment. One operator is working and he is trying to put the firefighting injections, and he is able to see that all, virtually he could able to see all the fire that is coming towards him. So what kind of error that will be inculcating in his actions, that will come out from this study. So that the human error probability will be computed. The way forward, strengthening safety research. Phenomena identification and ranking table. So this is very important to identify any phenomena that is going to get assessed. Now it may be based on the model, it may be based on the phenomena, it may be based on the model accuracy, it may be based on the information that is there. At AHWR, only one such part activity has been done so far. That was done in 2014, and that is purely done with respect to the severe accident progression of PHWR, since the order of uncertainty to determine the progression is very high. So only one such activity is there, but unless and until we do such activity with respect to different cases, so the order of funding in the research cannot be decided. All the research should not be done, only the most prioritized research to be done. So these are some identified research gaps that are accumulated with the AERB repository over the decades, I would say. I've listed down some things, like say, for example, critical heat flux estimation for 37 element fuel bundle. Today we are operating 700 megawatt, 500 megawatt with the 37 element bundle, but we do not have any such correlations with us. And we are banking on some assumed correlations which are not at all validated. So this is one of the priority research. Similarly, I would say this one, performance of natural circulation with inventory withdrawal. So if you have heavy leakage in the primary systems of any reactor, then the natural circulation becomes ineffective. No such systematic study has been done so far. So like that, they are with the repositories of AERB. I've just given the list. Now I come to the evolution of artificial intelligence-based technology. These are the applications, especially applications that are to be taken care in the future R&D, that is, which helps to transient detection, classification, predictions. This is with respect to O&M. Online sensor calibration and fault detections, trend predictions of operating parameters, control rod positioning monitoring with the neutron flux patterns, prediction of neutron flux prediction and power distribution, system level fault detection, component level fault detection. System level fault detection helps to recognize that what kind of anomaly that has come into the system. Similarly, it is the AI gives a direction for the digital twin systems. So with the digital twin architecture for fault diagnostic and prognostic, it has been found to be very effective. And currently, many industries, including Boeing, is also taken up the digital twin systems for their fault detection monitoring. The last slide. There's a heavily requirement of multiphysics tools that need to be developed at various ends. So thermal hardwick, neutronic, structural, coolant chemistry code, which is actually required for aging plant management. Then severe accident source term dose assessment. Then thermal hardwick, neutronic structure code for fast reactors also, for deck simulation. Today we do not have any deck simulation software or the tool. We are still banking on the external softwares. And system analysis and CFD coupled codes, especially for the boron mixing within the reactor pressure vessel or the calandria, we do not have today any particularly dedicated system analysis CFD coupled tools. Then multi-unit PSA tool development and usage. We lack over here also. So with this, I thanks for your kind attention.